Greetings and welcome to the Introduction to Astronomy. In this episode of New Discoveries in Astronomy, we will talk about how a compact X-ray telescope could help scientists create the first complete chemical map of the moon. So let's get started. How can scientists determine the chemical composition of an entire world when they can only collect samples from a few locations? That challenge has limited our understanding of the moon for decades. Although astronauts returned samples from a handful of sites and spacecraft have mapped portions of the lunar surface, scientists still do not have a complete picture of the moon's chemical makeup. Researchers cannot simply travel to every location, collect rocks, and analyze them in a laboratory. Instead, they must rely on remote sensing techniques that allow them to study the moon from orbit. And without a complete chemical map, important clues about the moon's formation and evolution may still be missing. The key idea behind this study is something called X-ray fluorescence. When energetic X-rays from the sun strike the lunar surface, atoms in the rocks absorb that energy and then emit X-rays of their own. Different elements produce different X-ray signatures. Oxygen emits one pattern, iron emits another. Magnesium, aluminum, silicon, and other elements can leave their own unique fingerprints. By measuring those signals from orbit, scientists can determine which elements are present on the surface below. In effect, the moon tells us what it is made of by the light it emits. The challenge is connecting enough of these signals to create a complete map. Previous missions produced valuable partial maps, but many regions remain poorly characterized. The problem becomes especially difficult near the lunar poles, where the signals are weaker and harder to measure. To address this challenge, researchers studied a compact X-ray telescope originally developed for observing Earth's magnetosphere. Unlike many space telescopes, this instrument weighs less than 10 kilograms. Despite its small size, simulations suggest it could perform an ambitious task. The team's models showed that a single telescope orbiting the moon could map 5 major elements across the entire lunar surface within about 2 years. Those elements include oxygen, iron, magnesium, aluminum, and silicon. A larger array of telescopes could complete the work even faster while producing higher resolution maps. The goal is not simply to create a better map. The real objective is to understand the moon's history. Different elements are concentrated in different geological regions. Their distribution records evidence of volcanic activity, ancient impacts, crust formation, and processes that occurred billions of years ago. By comparing where these elements are found, scientists can test competing ideas about how the moon formed and how its surface changed over time. In other words, chemistry becomes a record of history. This study reminds us that we do not always need to visit every location on a world to understand its past. Sometimes the clues are carried by light itself. A compact telescope orbiting the moon could transform faint X-ray signals into a global chemical map, revealing patterns that have remained hidden for billions of years. And by learning how to interpret these signals, scientists can continue uncovering the story of how worlds form, evolve, and preserve their history. So that concludes our discussion on mapping the moon's hidden chemistry. We'll be back again next week for another episode of New Discoveries in Astronomy. So until then, have a great day, everyone, and I will see you in class.